Hello, hello. I think everybody's joining now, but welcome to the webinar. We're gonna start soon in a couple of moments. So we let everybody in. Okay, so while the others are joining, I will shortly introduce myself. My name is Milana Sekulic. I'm the communication manager from HySEAS, and I'm happy to be the moderator and to introduce you to today's webinar. So this webinar, Direct Seawater Electrolysis from Challenges to Solutions, is organized by three sister projects funded by European Union and Clean Hydrogen Partnership. And we are very happy to talk about this topic today between the projects of Sea4World, SWEETHY, and HySEAS. We will tell you in a minute about what we're going to do. So on this screen, you can actually see the webinar agenda. And in the beginning, we will hear a bit about direct seawater electrolysis and its potential from Sea4World project coordinator Farhan Ali from VTT. And then we will continue with the project presentations. First, we will hear from Sea4World and Sasha Morlock from Fraunhofer IFAM. They will tackle the first challenge of seawater electrolysis, corrosion selectivity system efficiency. And then we will go into the presentation of HySEAS and Dr. Yagya Regmi from the Manchester Metropolitan University. This project will showcase the challenge of materials and system durability. SWEETHY will also deal with the same challenge. However, we will have a chance to hear from their perspective and their solutions, and they will be presented by SWEETHY project coordinator Olesja Danliv from RISE Research Institute of Sweden and Julian Fudge from CENMAT. In the end, we will finalize the webinar with the joint panel discussion, and you will also have a chance to ask the questions in the chat section of the webinar. I think we can also move on now to the introduction. So as we said, we will give a few words to Farhan Ali, the Sea4World project coordinator, to tell us a bit why we're actually here. And Farhan?
Yes, thank you.
Feel
Thank
free.
you, Milana. So the introduction to direct seawater electrolysis. So happy to see the European Union initiative and funding on those 4 projects in total on the seawater electrolysis. Then the idea for that one that each of us has different solutions to provide in the end, and we come up with a joint solution, hopefully at the end of those projects. Yeah. Next slide, please. So the seawater fed concept. So I will discuss quickly about VTT. Probably most of you know, but then still I can explain a bit what we do. And then direct seawater electrolysis, then how we approach, and then what would be the impact that we want to envision in that case, because the impact needs to be beyond those 3 years and then for future projects to come and the future development. Yes. So quick fun facts that about the VTT, that thinking ever grown coffee in the lab or making eggs without chickens, solving energy challenges. So that is one of the core thing that I work on, but also at the same time with the smaller nuclear reactors, or then the quantum computing is also one of the famous thing that we do at VTT as well. And next one. So most of you know that what VTT we do as the development and innovation for both the businesses and for the society, and one of the European leading research organization, which means that business, science, and technology are the core thing for us at VTT. And the main motive here is that thinking beyond the obvious, which means that to unlock new solutions. And one of the reasons for that one is the direct seawater. So to unlock those potential in the seawater that we can have through electrolysis. So here it's the main three things that I mentioned: the business, the technology, and then the partnerships. So we accelerate then tomorrow's growth by creating new startups. Then we also help to renew today's industries by developing the solution, and then also then strengthening the resilience within the Finnish society and also the public sector. So locally, then European level, and then on the international level altogether. So that's quickly that we are located in Finland, most of those locations. So I'm mostly based in the very south of Finland. And then we have the locations all the way through the central Finland up to the north but the biggest facilities and all the energy and hydrogen research facilities are in Espoo. For the C4 World project, so that's VTT is coordinating the project. Then we have Aalto University from Finland. We have two companies, Target Hydrogen from Estonia, and then we have Hydrolyte from Israel. Both are AEM and AEM related products suppliers. And then we have F6S from Ireland as the debt partner, and then University of Gdansk as the mostly working on the upscaling of the electrodes. And then we have the research institutes like VTT, Fraunhofer, and SIDAUT that are also working on the CFD modeling and then catalyst materials aspect in the seawater electrolysis. Yeah, so as I mentioned, it's a 3 years project initiative from the European Union. So the aim here is then the seawater fed electrolyzer concept. So without any chemical treatment, so mostly only the mechanical separation if there is, and then also understanding the different seawater feeds, for example, North Sea, Atlantic, and the Mediterranean. Sorry, the North or Atlantic and the Mediterranean and Baltic Sea. So quite many of those seas, and there is different composition of calcium, magnesium, and then also the chloride ions, which is one of the biggest impurities that suffer through the seawater electrolysis or challenges for the electrode structure and everything. Yeah, so the materials approach that has been done through or been going on in the literature is then, for example, those catalyst materials that are covered with shell structures, which means that to protect the corrosion, chloride corrosion, and other kind of impurities through the catalyst core. So that is one center point as well in the materials development, catalyst itself, and then also the coating or the shell around that catalyst material. Then the other important aspect is the harmonization. We have seen a lot of work through Europe on the alkaline and then also on PEM electrolysis that different protocols and harmonization has been done on those technologies, but then specifically for seawater, there has not been that much harmonized. So that is one other important aspect, that to harmonize the testing across different organizations and also between future project generations, and then also the industrial approach. It's always nice to focus on testing protocols that streamline the testing procedure. Then the cell and stack design. So that's during these projects, we have AEM concept as well. We have bipolar membrane concept as well. So both have their own merits and demerits. One of the challenges for the AEM membrane is the chlorine migration. So because of that one, the corrosion of the chlorine happens on the electrodes, and then the durability suffers a lot on the long-term performance as well. So that's why the cell and stack design is important. Another important aspect is the PDL design, and then also when it comes to from single cell to stack, then the bipolar itself plays an important role to go for more than one cell, or at least in a reasonable size of more than 10 or 11 cells stack. Then C4Volt and I think SWEETHY also, if I remember correctly, have the concept of the brine valorization. So instead of directly involved doing the seawater, integrating that process to already existing technology would be another important aspect to attract the industries and companies for the brine valorization, and then using catholyte and anolyte in that part with the AEM, or then the bipolar membranes, or the brine dialysis process as well. Then the impact, so quickly on the ripple effect. So wave one, we consider that is the direct seawater projects that has been funded through European Union, and those projects will lead those 3 years of intensive research work, improve the TRL, and then move beyond in the wave two, so 7 to 8 years now. And then that would be improving the AEM market, then novel membranes, and then also the different AEM manufacturer might adopt the solutions. And then also the wave three, which means that looking beyond 2035, that has more scientific, economic, technological, and societal impacts, that creating a new value chain of economy and industries in that part. Yeah. Yes, thank you. That was quickly on the direct seawater electrolysis. So we will more hear about details from each project perspective. Yeah.
Thank you, Farhan, for the introduction. And now we are going to move to the next presentation. We are moving to Sascha Morlock, a researcher from Fraunhofer IFEM, and he will talk about challenge one, corrosion, selectivity, and system efficiency. Sascha, you may take the floor.
Thanks a lot, Milana, for the kind introduction. My name is Sascha Morlock. I'm a researcher at Fraunhofer IFEM, which is located in Dresden, Germany. I'm happy to represent C4Volt here in this panel. So next slide, please. Next. Okay, so I guess we've seen this slide already. So next slide, please. And yeah, so the mission of C4Volt has different aspects. So I mean, first of all, it's especially in combination with seawater important to understand the materials. We will not only do our lab work as traditional researchers do, but we also will combine it with machine learning tools to help to speed up the process and to increase the understanding of the material and seawater interaction. Our goal is to be sustainable as possible, so we will develop materials and membranes that are PFAS-free, and we also want to reduce the load of the PGM catalysts. Ideally, we will work on PGM-free materials for the use in seawater. And we've chosen an AEM stack because we believe that AEM technology is the perfect fit for seawater electrolysis. On the one hand, compared to PEM electrolysis, it's way more stable, so the materials are not that prone to impurities. And on the other hand, we still have high current densities possible, which is important for offshore applications because space is limited there. As Farhan already pointed out, we will also develop some testing protocols, which are important to be able to compare and to really test the materials for the seawater fat electrolysis. And finally, our long-term approach is also to be more sustainable by using the brine not as a waste, but as a valuable resources for important and interesting metals. Next slide, please. All the partners work together to achieve that goal. Every partner is responsible to lead one work package. The project is coordinated by Farhan Ali from VTT. The core 3 work packages are package 3, 4, and 5 that interact with each other, where we develop the materials, do the upscaling, and finally, as said before, also do some computer analysis to study the poisoning in nature. And when we're done with our material characterization or material development, we will continue with testing in single cell and finally also in the stack. And of course, it's also important to have a look at the sustainability. So we also have work package 8, where we deal with different things regarding life cycle analysis, techno-economical studies, and so on. And as we do today, we're also heavily involved in the dissemination, communication, and exploitation. Next slide, please. So electrolysis has a quite long history. So about 250 years ago, it was first demonstrated that it's possible to use electricity to split water into hydrogen and oxygen. And it took then about 100 years to have the first commercially available alkaline electrolyzer. And then it took another 100 years to have the first seawater electrolysis, which was in 1980. You can see the Pourbaix diagram, which is especially important for seawater electrolysis, but I will talk more in detail about that in a minute. When it comes down to seawater electrolysis, the most important aspect is how to deal with the chloride in the seawater. So there's different strategies. One is, for example, to use a blocking layer to avoid the contact between catalyst at the anode and the chloride. There's also some options like asymmetric feed, and latest there's also the approach of using an additional membrane in order to avoid the contact between seawater and whatever happens in the electrolyzer. But I wouldn't consider that direct seawater electrolysis, and since this presentation is about direct seawater electrolysis, I won't go into detail here. Next slide, please. Yeah, so this is the Pourbaix diagram. So as you can see here, we have this green curve, this green line. Everything that's below that green line means we can produce oxygen, or in other words, oxygen evolution is from a thermodynamical point of view always favored. However, there's a side reaction is possible if the over potential for OER is too high. And depending on the pH, we see different side reactions, which is especially critical for low pH, because we have chlorine evolution, which is possible below a pH of about 2 or 3. And we also need only a very low over potential to achieve that undesired chlorine evolution. So typically we go to higher pH values where you have about 500 millivolts till we see this side reaction. Next slide, please. So different strategies have been exploited. One example here in the literature is where they use the triple protection strategy to reduce the corrosion, where we have an outer layer of cobalt phosphate, then there's a dispersed magnesium oxide nanoscale, and finally a third defense mechanism is to use a special structure to reduce the forces that are caused by the bubbles. And if you apply just one of these protection mechanisms, you can see that there's a degradation that happens rather soon. If you have all the 3 mechanisms, you can run at a constant voltage for about 3,000 volts. Next slide, please. Transpassive dissolution is also an important aspect when it comes down to corrosion in electrodes in seawater electrolysis. Transpassive means that at first the electrodes are stable, but if you apply too high potentials, then some elements can be leached out. This is especially critical for molybdenum and chromium. And in some cases, you can see a secondary passivation, means if you reduce the voltage again, the solution is stopped and you get another passive layer. However, this is not as stable as the initial passivation, so it's still undesired. Next slide, please. One example that you can see here for enhanced passivation is when you add magnesium. So as you can see here on the right-hand side, this purple bar indicates that the window that can be used for the working in seawater is increased significantly by the application of this magnesium-based passivation. On our right-hand corner and in a lower graph, you see that if there's no catalyst, we don't see any current, and as soon as we add the catalyst, we also see a current. That means in principle the basic material is stable. Next slide, please. There's different strategies to avoid corrosion after all, and also to increase the selectivity and efficiency. So there was a study that compared different ways of feeding electrolyte, KOH, seawater, and a mixture of KOH and seawater into a cell. As you can see here, the figure A is the conventional setup, which is more or less the AEM approach. That also has the highest current at a cell voltage of 1.7 volt, as you can see here on the left-hand side. However, this blue curve, which is F, that means we have a pure seawater feed at the cathode and a pure KOH feed at the anode. It has a similar performance of the setup, and it's also very stable performance. So by using this asymmetric feed, it's likely that you can have a good performing system, but also stable system. And this is also what we're doing in C4 So next slide, please. Yeah. Thanks a lot for your attention. And I'm looking forward to the discussion later.
Thank you so much for your presentation, Sasha. And now we are moving on to the next presenter and also the next challenge. So right now, Yager Ragmi from the Manchester Metropolitan University will present HySEAS approach to challenge 2, materials and system durability. Yager Ragmi is the reader in energy conversion and storage and in the Manchester Metropolitan University, and I will give him the floor now to tell us a bit more and present his slides. So Yager, it's
Thank
your
you,
turn.
Milana. Next slide. Thank you. So I am representing HySEAS. As you are aware, European projects are complicated beasts. We have a lot of people, a lot of institutions working on the project. We have 8 institutions from 6 different European countries. And different partners. We're doing things from materials preparations, integration into devices, doing computational simulations and stack testing. Different partners are involved in different. I'm not going to go into the details of every aspect in a 10-minute presentation, but I will try and cover the overall activities. Okay. So as Sasha just mentioned nicely, using the Pourbaix diagram, what is the real challenge for seawater electrolysis, right? The real challenge is really trying to enhance oxygen evolution reaction over chlorine evolution reaction. He showed on the Pourbaix diagram, thermodynamically, oxygen evolution reaction is favored over chlorine evolution reaction. What is even more challenging is as you start increasing the cell potential, the overpotential for OER and CER or chlorine evolution doesn't increase linearly. At higher potential, the overpotential for chlorine evolution is a lot smaller than oxygen evolution reaction. That's why at higher cell potential, chlorine evolution reaction can overtake oxygen evolution reaction. So our aim is to try to overcome this problem by modifying materials or synthesizing new materials, controlling the microenvironments within the device, and the other aspects that I'll show in the next slide. Next slide, please. Okay, so our approach is to, instead of using either PEM water electrolyzers, that's on the right-hand side on your screen, or AEM water electrolyzer that Sasha just discussed in front of us. Our approach is to use something called bipolar membrane water electrolyzers. So in bipolar membrane water electrolyzers, you use both AEM and PEM. In the diagram on the left-hand side, AEM is AEL, anion exchange layer. PEM is CEL, cation exchange layer. Now, in order to bring this PEM and AEM together, we also have to put a catalyst layer between the PEM and AEM in order for the device to work. We call this water dissociation catalyst. This water dissociation catalyst is actually where the water splitting takes place. The protons go in one direction towards PEM, hydroxides go in the other direction toward the AEM. What this allows you to do, it allows us extra controls. We can control which way the ions are flowing, which way the impurities are flowing, at least in theory. And for the most part, HySEAS project, our aim is to demonstrate that all these knobs can be tuned to improve seawater electrolysis over chlorine corrosion. Next slide, please. So where are we in terms of seawater electrolysis? This is a project I was involved in many years ago now. So what you are seeing here is we are here comparing between performance of PEM versus bipolar membrane electrolyzers. If you look on the figures on the left hand side, the B on the left hand side is electrolysis using PEM water electrolyzers. The one on the left hand side, A on the left hand side, is bipolar membrane water electrolyzers. I know there is a lot of stuff on the screen, but the take home message here is that when you use bipolar membrane water electrolyzer, the potential for water electrolysis definitely increases because you are using two membranes, you are increasing cell resistance, so on and so forth. But our hope, and which we demonstrate here, if you look on the right-hand side, the two graphs on the right-hand side, you see that bipolar membrane electrolyzer, although the potential is higher, it's stable for a much longer time when you start feeding seawater instead of purified water. Next slide, please. So what have we done beyond what I call the state of the art in seawater electrolyzers is that we started looking at each and every component in the bipolar membrane electrolyzer, starting with the water dissociation catalyst. The first thing, the baseline where almost everyone starts is titanium dioxide. We looked at different types of titanium dioxide, anodized, rutile, brucite, different loading of TiO2 onto the water dissociation catalyst layer. And as you can see from here, when we started really early on, the DI water dissociation, the bottom right graph on your screen, when you feed just DI water, the cell potential is slightly above 3 volt. But as soon as you start, this is simulated seawater now. We're calling 0.5 molar sodium chloride simulated seawater. The potential, the cell potential increases quite rapidly. Next slide, please. So we started looking at different AEMs, different PEMs, catalysts, both cathode, anode, and water dissociation catalysts. Just a quick example, if we change the AEM membrane thickness, so Piper ion from Bersigine, we looked at 4 different thicknesses, but I'm just showing you 2 here. When you use 20 micrometer thick Piper ion 20 versus 40 micrometer Piper ion 40, you can see that the initial performance, the figure on the left hand side, is pretty much similar. There is slight cell potential increase when you use 40 micrometer membrane, but the real thing to really look at is if you look on the right hand side figure, when you use Piper ion 20 versus 40, the degradation over the test period is quite a lot. When I say test period here, just for clarity, we're running simulated seawater for about 2 hours. even within that time, you can see the effects of using different, just the thickness of the membrane itself. Next slide, please. In terms of PEM optimizations, we used the standard Nafion 212, although it's is thick, and we also use Nafion XL, which is similar to 212, except that it has mechanical fibers inserted into the membrane for mechanical stability. Similarly, we also looked at other options, something like Nafion HP, and you can see Nafion 212 and XL, they perform very similar, and you can get to 500 milliamp per cm square below 3 volt cell potential. HP, on the other hand, doesn't work as well for us. This is just a flavor to give you what we are doing in order to select different components. Next slide, please. Then, in terms of PEM optimization, we also looked at different durability protocols. As Sasa mentioned and others mentioned before us, it's really important to make sure we are able to compare performance from one lab to the other, one country to the other, and we are using EU harmonized protocols. And depending on how you break in your bipolar membrane electrolyzers, things can be stabilized even without changing any components. It's just the way you run the electrolyzer can make it durable versus unstable. Again, you can see on the right-hand side figure, we are able to bring the cell potential slightly below 3 volt at the performance level we need to meet by the end of the project. Next slide, please. The other thing that I want to highlight here is just selecting the right component is not the only knob you can turn in these things. There are different ways. The way you integrate your component into your cell, the way you run the cell. For example, this is well known in electrolysis area, but I just want to highlight. Just like in PEM or AEM electrolyzers, the cell compression makes a huge difference. What you are seeing in the graph is the one that said 0% has no, the MEA, membrane electrode assembly, is not compressed by using different gasket thickness versus your MEA thickness. By the time you go from 0% to 10% compression, performance increases by a lot. And by the optimal cell compression we found was 30% compression. And as you can see, now we can achieve this 0.5 amp per cm square at about 2.8 cell voltage, which is already exceeding the final performance we need to demonstrate in the cell. Just like that, what we are doing is we're just like the cell compression, we are optimizing each and every aspect of a MEA cell and stack level, and we will hopefully be able to share the final results in the coming months and years. Next slide, please. So that's the experimental side of it. We are guided by computational simulation. Just as an example, we look at different scales. So on your left-hand side, we are looking at what happens when your oxygen molecule or any reactant adsorbs on different active sites of your catalyst. For example, we're taking 5 iridium atoms. We're assuming that the catalyst is composed of 5 iridium atoms at different geometries, and we're looking at what happens when adsorption occurs at different iridium sites. From that atomic scale, we go all the way to centimeter or meter scale, at least in theory, and we look at what happens to, on the right hand side, what happens to the water as it approaches, let's say, the electrified interface between your catalyst, membrane, and your transport layers. So we're guided by computational models so that we have a feedback into our experiments too. For example, the computational model guides us how thick TiO2 level between the PEM and AEM needs to be. All right, next slide, please. So thank you for your attention, and I'll be happy to answer any questions and participate in the discussions to follow. Thank you.
Thank you, Yaga, for your presentation. And now we are moving on to the next presentation. We are still on the same challenge, but now we are going to hear about a different approach from the SWEETHY project. And here to talk are SWEETHY project coordinator from RISE Research Institute of Sweden, Olesya Daniliv, and Julian Fudge, polychem chemist from CENMAT. I give you the floor. I think Olesya will start,
Yes.
or
yeah,
okay.
Sure. I will start, and then Julian will help me with the membrane part. So please go to the next slide. Yes. So I'm going to talk about SWEETHY. The full name is Direct Seawater Electrolysis Technology for Distributed Hydrogen Production, and specifically about this challenge of materials and system reliability. Let's go to the next slide. As it was mentioned before, our project is about ion exchange membrane water electrolysis technology to produce green hydrogen. And we are also looking at several levels of the system in order to tackle different durability issues, but also other issues that come together with seawater electrolysis. So we are looking at the cell level, where we're trying to develop different components and materials, including membranes, electrocatalysts, bipolar plates, and PTLs. Then we're also looking at the system level, electrolysis stack. We're developing intermediate stack and bigger short stack, which will be the final prototype, operating with seawater in Italy, in Messina, at our partner site. We're also looking at how to couple our seawater technology to other industries in order to find the industrial symbiosis between seawater electrolysis and other industries. But then I will describe even more these parts in the next slide. So there are three main approaches of our project, and as you see on the right side, the two first approaches, they will specifically define the materials and system durability work in this project, and which are one, material development, and two, electrolyzer configuration. Then we also have another approach, the third one, which is the sustainability analysis, but it has indirect coupling to material system durability. That's why I will not talk much about this today. But of course, you can read much more about our project at our website, which is sweety.eu. There is also a YouTube webinar, which I presented several weeks ago. It's there all the time if you find YouTube SWEETHY webinar. So you can hear a little bit more about SWEETHY project. But let's look what we are doing at the two first approaches. So please click next. Just as the other projects, we are going from TRL 2 to 4, and that's why you see two big boxes in the slide. So on the material development level, we are working towards development of PGM-free, so platinum group metal free, selective and durable catalysts, first at a small scale, and then when we are going towards TRL 4, we are going to upscale them. Then we are also developing the new type of ion exchange membrane with high ion selectivity and high anti-fouling properties, because that is very important when we are working with impure water. Again, we are working at first with a smaller scale, and then we move to the scale of active area 120 centimeters square, which will be inserted in the final prototype. Again, the third part of material development is that we are developing the anti-corrosion coatings for bipolar plates and porous transport layers. And again, we are going from smaller scale to higher scale by the end of the project. So this was the material development part, the first approach. Approach 2 is electrolyzer configuration. So we are testing all the developed materials on single cell level. Then we are working to the short stack level, intermediate size, and then we are going even testing our materials in the final prototype, which is a bigger stack. By doing this, we can confirm that all the developed materials, they are durable, they show their reproducible performance, and we can be sure that by the end of the project, all the results on the new developed materials, they are true, and they can operate with seawater. And also, one important part within this block, electrolyzer configuration, as Farhan mentioned, we will study the byproducts from the electrolysis, which include brine, but also the precipitates, different salts that precipitate during the seawater operation in electrolyzer. Yes, and the third approach, which I will not go into details about today, but sustainability analysis includes that we are doing the screening activities regarding the life cycle assessment. We are looking into industrial symbiosis between seawater electrolysis and other industries that can reuse the byproducts from SWEETHY electrolyzer. And by the end of the project, we will perform the full environmental and social LCA together with a techno-economical assessment to understand the cost of the whole system. Next slide, please. So within the first approach, the material development, I will present three parts. The first one is about catalysts. We are having several approaches for fabrication of electrocatalysts, chemical and electrochemical approach. This also helps us to have the broad design of electrocatalysts, which I remind they are platinum group metal free catalysts. We can also receive the catalyst, and we can optimize different properties of this catalyst by these approaches. Regarding, so during this 1.5 year of the project that has passed, we see that we achieve good scalability of this catalyst. We are very attentive towards high purity, reproducibility of the results. And here you see some examples of 2 out of 3 project partners who work on catalyst development. So, for example, you see on the left-hand side, there is the image, SEM images of the hydrogen evolution reaction catalysts. They show that the catalysts are homogeneous, scalable, and we have reproducible results when we test them for electrochemical performance. On the right-hand side, you see the images of and performance of the electrocatalyst developed by SINTEF, another partner in the project. In this particular example, it's about the anode catalyst. Again, if you want to know more about the details about this catalyst, I refer again to our website where we have the deliverables being published. And also, if you want to know the details about the catalyst, we can also make you in contact with these partners. The next slide. One of the latest results that we started to test our catalyst in seawater in a single cell level. And it's the third partner within this group of partners who developed the catalyst, CNR Italia in Italy. And they show that the catalyst that they developed, it performs well and for more than 1,000 hours in seawater, reaching the degradation lower than 15%, which lies well in the key performance indicator that was defined in the beginning of the project. Next slide, please. Within the first approach of material development, now we're going to talk about membrane, and I leave the floor for Julian.
Yeah, thank you very much. So on the previous slide. Yeah, thanks. So at SENMAT, we developed membrane for AM. Our developed membrane is called IronFlex. So it's a PFAS-free material with high conductivity. So you can see that it's giving about 2 volts at 2 amp per square centimeter. in 1 molar KOH at 50 degrees using our own PGM-free catalyst for the anode and cathodes. And here we are using stainless steel bipolar plate. Standard test is here running 2000 hour with degradation matching or way below actually the target of the project. But here I will show only test in 1 molar KOH, so we don't have seawater. So we are first testing the membrane alone to confirm their stability, and then we'll move on to seawater with our partner at CNR in Italy. So on the next slide, we show that one of the challenge that we want to tackle is selectivity of the ion in the membrane. So we would like to have hydroxide passing through and no other ions, mostly chlorine, of course. So one approach is to use fillers, and one approach is to coat our membrane with a nanolayer. If you go to the next slides, I show two different membranes that were additivated with 5 and 10% of filler. So in terms of performance, we're in similar range, around 2 volts at 2 amperes per centimeter, a little bit below sometimes. What got interesting is that we realized that 2000 hour similar performance curve, but let's leave them running. So now it's 6000 hour running, and what's happening is that from 2000 around 2500, then it stops degrading. So right now we have from 2500 hour to 6000 hour no degradation, which of course is also something that we will bring to the next part of the project when we come to seawater. Longer tests might be also interesting because this is when we see stability. On the next slides, another approach is to apply a nanolayer of another polymer that would block some of the ions. So now we are starting this test, and performance is quite matching. We're losing a little bit of performance in the high current density, but this is expected on a polymer to polymer. Polymer on polymer coating gives a bit of resistance. But interestingly, in the stability, it's improving. So we are now just 400 hours, so it's relatively short test, but in the next, we'll evaluate that in the next 1000 hours. But it's definitely improving, so lower voltage. So this will also be, all of our material are then transferred to CNR, who is doing really extensive tests on permeability, and also they will do seawater testing, as Alicia already shown. So yeah, I think that was my last slide, I believe.
Yes, and I can continue with the next slide. The last part of the material, in this presentation part of the material development approach, which we are doing to tackle the durability issues and of the components, is that we are developing the anti-corrosion coatings for BPP and PTLs. We will also assess the risk of galvanic corrosion in confined areas, and we will evaluate the corrosion resistance of pipe materials, which considers the balance of plant of the electrolyzer. Next. So far within this task, we performed the corrosion study of uncoated BPP and PTL, and the same studies on coated BPP and PTL are ongoing together with the development of anti-corrosion coatings. That's why so far I can just show the results on the uncoated BPP and PTL. This is also a deliverable, public deliverable at our website. So you see in the table the metrics of substrates, metallic substrates that were studied on corrosion behavior, both in anodic and cathodic polarization in 1 molar KOH and in seawater, or alkaline seawater. Next slide, please. And now we are reaching the second approach, which is electrolyzer configuration. So within this topic, we are, again, as the other project, trying to harmonize the single cell activities, because we have a lot of partners that are doing single cell testing of their components, as you see on the slide, the testing partners. And that's why we have the single cell, which was developed by our partner Propulse. That is quite unique single cell because it's operating under hydraulic compression. It means that the whole cell is under compression, which leads to homogeneous pressure distribution within the cell. It also helps to make the effective heat management in the cell, and you can also achieve modular design when we move to the stack level. What is also important here that, for example, the frames within the cell are made of polymer PEEK, as you see from the image of the cell inside, which also tackles the corrosion issues when working with seawater. Next. Then electrolyzer configuration moves to the intermediate short stack. We call it 5-cell stack. It's under development now, and HySEAS will soon start testing the seawater operation within the stack. As you can also see the image under the picture, how the stack looks like, that each cell is like inserted as in a pocket within the hydraulic liquid design. But that is not the final prototype. The final prototype is something that is not visible yet, so please next. It's the goal of this and next year of the project, when our Propulse partner is developing the stack for 10 cells. And this will be our final prototype, which will be installed in Italy, where we'll test all our developed materials under long-term operation, more than 2,000 cumulative hours with seawater. Yes, so with this, I would like to thank to all our partners that are involved in the project, 9 partners from 7 different countries. And just one thing more, next slide, which is not concerning the durability issues directed to our project, but it's about the event that we are organizing about the durability issues in low temperature water electrolysis. It will happen in Stockholm in October this year. And at the moment, all the abstract submission will be open just for poster presentations. But if you would like to be there and be part of this research community who will present their visions on durability issues in mostly PEM and IM electrolyzers, so you're welcome to visit again our SWEETHY website, where you find more information about this event, or directly contact me or the symposium email. Thank you.
Thank you, Lesia, and thank you, Julian, for this presentation. And now we are moving to the joint panel discussion between all 3 sister projects. We are a little bit above the expected time schedule, so we will have a bit of about 30 minutes for the panel part, but also we will remind all the audience that they have the chance to also ask the questions in the chat section of the webinar. So feel free to post the question there, and we will answer them once the panel discussion is finalized. So I will give the floor now to Farhan Ali as our discussion moderator. Farhan.
Farhan, you're muted.
Apologies. Apologies. Yes.
Yes. All right. I guess, yeah. So in the panel discussion, I will post the topic to discuss, and then I will ask opinion from each of the expert from here. And so my first question, or first point of the discussion that I would like to know the opinion from the experts, is that if you can identify one obstacle that you think that is between direct seawater electrolysis and the commercial deployment, or instead of commercial deployment, maybe increasing from low TRL to high TRL, then what do you think that obstacle will be, in your opinion? So we start with Sasha.
Yeah, very good question. I mean, only if we're honest, and I mean, we've presented our projects. We're currently targeting TRL4. So in principle, there's more than just one single obstacle in our way, but I guess the most important one would be the membrane, because we can draw many different or nice graphics, at least for our concept. If we want to have this cathodic feed with pure seawater and anodic feed with pure KOH, that mainly depends on the membrane. So that would be, if I had to identify one single part of our electrolyzer, this would be the one that's most critical. But that doesn't mean that if that works, there's no more other problems. But I think the other problems should be easier to solve.
Yes, thank you, Sasha. So I will come back to this membrane later on as well, as one of the participants has the question on that one. So, but first we go to Yaga for the opinion on that.
I agree. Membrane is one of the most critical aspects. But what I think, if we focus on what's going to drive the technology towards commercial deployment, I would say it's actually the reproducibility and repeatability of devices, materials, and systems that we make. Because if somebody is going to invest in the technology, they want reliable, reproducible data. This is not unlike in other scientific fields. We are suffering from reproducible, reliable data and test result, test analysis, so on and so forth. That goes true for seawater electrolysis, as with other electrolysis as well. We have seen thousands, millions of publications for new catalysts, new materials, so on and so forth, but very little attention is actually given to how these materials are integrated into devices, because it makes a difference. And the drive should not be to show that your catalyst breaks a record, right? With a performance of durability, it should be that can the scientific community, can the commercial companies, can they actually reproducibly demonstrate the performance or durability as well? So I think that's what's hindering. I'm not saying the material challenge is not there. I'm not saying the other challenges aren't there, but we are really suffering from, in my view, from reproducibility and reliability of different kind of tests.
Yeah, yes, Olesia and Julian, please.
How's that? Well, in my opinion, the durability of these electrolyzers working with seawater, that is the problem, and not only electrolyzer, but the whole balance of plant, because corrosion will be quite high if we work directly with seawater without any purification before feeding the seawater to electrolyzer. So we will need to have a lot of coupling to marine research, because not only chlorine, but also all the bio materials or bioorganisms that are in seawater, these are main impurities, basically, which will influence the durability of all the components, all the materials in the system. And without proving, not on the lab scale, but in reality, that we have a durable electrolyzer, big electrolyzer, no one would like to commercialize this kind of technology. So yes, durability, and it includes, actually, it's not only one obstacle, it includes everything what we described today.
Thank you, Alessia.
Julian, are you on the same line, or?
Yeah, I think so. I mean, as polymer chemists, I agree that membrane is it needs to be really reliable, especially if we use this kind of differential feed. So this is a big challenge that we are trying to tackle as well. Yeah.
Yeah. The other aspect that I would like to ask is for example, the solutions that we have today. What do you think the research, technology, and innovation gaps that needs greater attention over, for example, next 5 to 10 years? Yeah. So any insights on that one?
If you want, I can start. I think that we are now looking far beyond in future, and right now you mentioned that which solutions we have today, they are still on the very low scale level. Go upscaling, it includes many challenges. So that's why maybe upscaling that is the biggest problem at the moment, because we test upscaling also at the lab level, but not on the industrial level. So as soon as we will test these solutions, or what we think is a solution at the industrial level, and we see that it will be taken by the industries and scaled up and used, not only for seawater electrolysis, but even for other industries, then we can say that, okay, then these solutions are good, and we may move to the system level, okay, how we insert all the developments at this small level in the big industrial system. So yeah, scale up is a very important step, which we don't have a clue about at this stage, I think.
Yeah, I fully agree on those. There are very small things that needs to pay attention into those the huge system. So I would like to ask from the same thing from Yagaya.
So in my view, if we are going to look 5, 10, 15 years down the line, one thing we need to look at, which we haven't discussed in all the projects here, is the electronic and electrical aspect of it. We're assuming that seawater electrolysis, like all other water electrolysis for hydrogen production, they are going to be powered by renewable electricity. The quality of electricity that's coming into the electrolyzer from renewable sources, be it solar panels, be it wind turbines, that has to be reliable. That has to be controlled, right? So things like controlling the harmonics, so that the incoming electricity doesn't fluctuate too much. That aspect doesn't get as much attention as it should. Why does that matter? I'm a material chemist. I've spent most of my academic life synthesizing, testing catalysts. Now, if we are going to build an electrolyzer and expect the electrolyzer to filter out all the noise that comes from the incoming energy source, electric source, we are doing a disservice to our system. Instead, if we can put in quality electricity into our electrolyzer and filter out all the damaging aspect of the energy, that's another way to make our electrolyzers perform better, durability for a long time. So I think that is an aspect that needs quite a bit of attention.
Yeah, indeed, it is quite intrigued to know that the system electronics play a huge role in the future systems. Yes, Sasha.
Yeah, very good points, and I like to agree on them. But I would also highlight that we should, if we're talking about the future developments for seawater electrolysis, I think beyond the pure electrolysis. I mean, typically, if we're asked, we would say our product is hydrogen. Technically, it's also oxygen. But furthermore, we should think whether we can provide some more products or other features that might also be beneficial beyond hydrogen production or oxygen production, which could be, for example, the brine valorization that we also want to tackle in C4 so that we can produce some metals or some other components in the seawater and that we can extract them to also sell them as a second product, because that helps, on the other hand, to reduce the costs for the hydrogen if we have a second product that is also valuable. Because I think this is the only option to be cheaper doing seawater electrolysis compared to first a pre-treatment step by, for example, osmosis, and then doing conventional electrolysis. Finally, at some point, we need to be, at least for certain applications, cheaper than the competitors. Otherwise, nobody will do it.
Thank you, Sasha. So final aspect of the discussion before we go to the question answer, we have also the couple of questions as well from the audience. But before that one, my final take is, what do you think the single development could be, either technical, industrial, from the regulatory related, that you think that will accelerate the direct seawater electrolysis hydrogen production? So Sasha or Alessia, you can, any of, if you think.
I can start.
Yeah.
So I'd say, and in that case, it's really not in our power to change anything about that. But seawater electrolysis is most likely combined with offshore wind. So the more offshore wind we see and the further away from the coast, the more likely we'll also see a lot of need for seawater electrolysis.
Yeah, thank you, Sasha. Alessia.
Yeah, you mentioned a regulatory aspect.
Regulatory, industrial.
It's made more political, I would say, that it regards on political views on the if we promote the production of hydrogen by any possible technology, including seawater electrolysis, then apparently that will help developing technology as well. But if there is no promotion from political side, then of course it will not develop so at the same speed as it could be. Then maybe there are some other regulatory aspects, but I probably do not have the good overview over that.
Yeah. It was any kind of like a single most development aspect you can think, regulatory, technical, whatever you think of it. But yeah, indeed, political willingness is very important for sure. Yes, Gaya, in your opinion?
Yeah, I completely agree. It will come down to how much willingness the policymakers have, different governments have around the world, because although we talk about materials, devices, and so on and so forth, right? If we look at the cost of hydrogen, the end product hydrogen, electricity, renewable electricity still accounts for 50% of the cost, right? So as policymakers, they should, if we want this to be possible, this technology to be really possible at scaled up level, we have to ensure that the cost of renewable electricity remains low. The cost is coming down. Hopefully it keeps coming down for the next 20, 30, 40 years. But policymakers have a role to play here. They have to incentivize, just like I'm not trying to beat up on hydrocarbon industry. They have enjoyed a lot of protection and incentives over the century, right? Similar kind of incentives should be available for renewable electricity as well, all around the world. I think that is what will incentivize take-up, just not for seawater electrolysis. Of course, seawater electrolysis is a lot more difficult than PEM and AEM electrolysis or alkaline water electrolysis, but it will filter down to seawater electrolysis as well. can protect the price of electricity or future-proof the price of electricity. I think Sasha had a point. He was raising a hand.
I just slipped on my
Yeah. Yeah, Yaga, that was very good point to know the incentive indeed that the hydrogen production through electrolysis needs incentives. Similarly, the hydrocarbon industry have enjoyed for a long time. Yeah, I have also a couple of questions that the audience has asked. So I will start with Yagaya on the membrane degradation. So the question is that the audience wants to know the membrane degradation in actual seawater electrolysis rather than on the simulated seawater. Is there more data than on the actual seawater?
I mean, there have been some demonstration in scientific literature for the most part. We have
But also
shown,
from your perspective, or like at least in your institute or in the University of Manchester.
yeah. I mean, as part of the project, all four projects that were funded, we do have to demonstrate performance in actual seawater.
Yeah.
And there are reports. We test them all the time. It's just that if we build a system and expose that poor system to actual seawater in the front, it's really hard for it to understand what's going on. That's why we have to simplify it, break it down, and then we introduce different elements of actual seawater over time, so that we can fine tune all our components and system. Ultimately, at different stages, of course, we do feed seawater, direct seawater, and see what the performance is like. And it's, to be honest, it's not really that different from simulated seawater. Of course, we are assuming here that most of the biomatter and solids have been removed from seawater. Of course, we can't really feed the seawater without any treatment, but the performance is quite encouraging, I would say.
Yep. Thank you. I would take that same question to Julian as well, even though you mentioned that it's been done in KOH tested. So, but what do you think or you anticipate?
Yeah, so we actually, I think Olisha showed some cell testing. It was actually, if my memory is good, it was actual seawater. So we do some tests with surrogate seawater in the project, but our partner in Messina, in CNR in Sicily, they do collect some seawater. And they did tests with minimal purification, so filtration, of course, because yes, you don't want some solid. We also expect that the KOH environment would mostly kill most of the living organism, but we still have to deal with all this biomass that would still be there, especially. So we have also a part of the work in the membrane development, which is about anti-fouling, which needs to be tackled. But I think it will be tackled also at the system level, because fouling is not just at the membrane, obviously. So I think that in terms of performance, stability, maybe on short term, we would not see so much difference between surrogate and real seawater. But when we run thousands of hours, then this is where it might get different. So this is something for either the end of the project or the next project.
Yeah. Yes, I do agree. Sasha, do you have what's your opinion on that?
Well, I wouldn't consider myself a membrane expert. So we are dealing with the metallic components in an electrolyzer. That's our expertise. So I don't wanna comment on that.
All right, Alicia, I guess you have yeah.
No, I just want to complete what Julian said, because he referred to what I showed. It was what I showed in seawater. It was the benchmark material, but with the developed catalyst in the project. And then we will test the developed membrane within the project a bit later with seawater. So far, we tested only with KH. So the question was, yeah, I cannot comment on how our developed membrane is performing in seawater yet. This will be the result within several months' time. We will start testing seawater.
Yeah, exactly. Thank you. And the next question is, I will start with Alicia, with you, is that what do you think, or of course the whole panel, I will go one by one after, that what the panel think about using NaOH, sodium hydroxide, instead of KOH for the anode side. This would perhaps make it possible to produce the NaOH at sea. That's the question. Yeah.
Yeah, we had these discussions in the project as well. This is an interesting question, but it may be referred to the cost even of KOH or NaOH. This we need to check. I don't know actually if the cost is similar or there's much difference, because apparently we need to use for AM electrolysis, we will need to use base to make the whole electrolyte basic. So of course it will be a big quantity. So we need to see the cost level of NaOH and KH. But from the chemical perspective, as it was mentioned in the question, this is something that we have not thought of exploring. But this could be interesting. But it may be also connected to maybe the yeah, I know. Yes, we need to see if there is room to explore even this part of changing the base solution.
Right. Yes. Sasha, same question to you.
I mean, it's definitely a nice suggestion. As I've said earlier, I think we finally need to find more products than just hydrogen, so this could be an option. In principle, I would assume you would end up first with sodium chloride, not sodium hydroxide solution. So typically, if you want to produce sodium hydroxide, you would do chloralkali electrolysis, which would then also mean you produce chlorine on purpose. This is another story, but in principle, yeah, I mean, why not? I would believe them for the materials. It shouldn't be a problem to operate in sodium hydroxide solution instead of KOH.
Thank you, Sasha. And Yaga, do you have any?
Yeah, that's a great question. Like previous panelist mentioned, right? There is a long established history of chloralkali industry while producing chlorine. They are also producing sodium hydroxides lye. So that's exactly where we started with our project, and that's the reason why instead of using any other salt that we could have chosen, we picked sodium chloride as the simulated seawater, 0.5 molar sodium chloride for simulated seawater. Now, directly addressing the question, would there be a difference between KOH and sodium hydroxide per AEM water electrolyzers? There are small differences. Julian and Alicia probably can comment on this. It does affect membrane slightly differently because sodium cation versus potassium cation has a different hydration cell that has a direct effect on how different functional groups in your AEM water electrolyzer interact with your base. But the difference is not too great at this point for us to have to make a choice between KOH versus sodium hydroxide. I could be wrong. Julian probably is better placed to comment on that.
Well, I think that yeah, all you said is right. What we would probably see is a slight drop in performance because usually we get lower conductivity, and as you said, with the hydration. So this would, considering that already with seawater we get a drop in performance compared to AM, that we would probably have some coatings necessary to protect all the metals, which could also give a little drop in performance. It depends how much we want to add on. So eventually it could be tested. Yes, I think that price-wise, it should be cheaper to use NaOH, but we know from AM that the price of the KLH, it doesn't really matter. I mean, we talked about price of electricity. This is the main factor, obviously. So yeah, but it's an interesting area that we should consider open. Yeah.
Yeah.
What I can also add, maybe just the idea, maybe it could also influence how much precipitates we form. Maybe it is because we are working in high pH, and when we use different base, it could influence how much precipitates we can form with if it's KH and NaOH. So maybe that's why also everyone goes for KH, because we can precipitate better some salts with KH. That could be also a reason why everyone looks in KH.
Yes, very good opinions on that one. One final question that I have, I think, from the audience. Are there standardized protocols for benchmarking catalyst materials in single-cell testing? We frequently observe significant lab-to-lab performance variations for identical materials and want to ensure reproducible comparisons. So, Alicia, we can start and then we can quickly get a comment on that.
Yeah. Actually, during the presentation of Sasha, I think you mentioned that you use the standardized protocols, but I didn't know about that they exist. So you could explain more. But what we were trying to harmonize within the project, so each partner is following the same harmonized protocol. Then that could be actually a good point for this, as we call our cell-sister projects, to look how everyone is doing the single-cell testing between the projects, and to see if at some level it could be harmonized and addressed to the European Commission, that this could be the goal for harmonized protocols for the seawater electrolysis operation. So I agree there should be standardization, but I haven't heard that there is one. And of course, there is no for direct seawater electrolysis, but if there is one for pure water electrolysis, Sasha, probably you could tell me more.
Yeah, so there's no official protocol, at least not that I'm aware of. So we've also just within the consortium agreed on certain standards. But as you've mentioned, I think all of our sister projects, we should come together and make suggestions for a joint protocol that everybody can use to have comparable results. One aspect that might not be possible to harmonize is the composition of the electrolyte, because that also strongly depends on the feed that's used. So for instance, you use alkaline seawater, we use pure seawater. So in that context, it always needs to be specified. But I think that's just one minor aspect in the whole context. And as Yaga mentioned in his presentation, also if you see differences between different labs, might be, for example, also because of how the setup was done. So if you have different pressure, how you assemble the cell, that also leads to different performances. So it's not only about the testing protocol itself.
Yeah, I do agree that could be actually a very good outcome from all the sister project collaboration to have this kind of a standardized protocol, even to EU and for the public as well. Yes, Yaga, please.
So there are I agree. There are no published or endorsed government EU endorsed harmonized protocols for not definitely not for seawater electrolysis. We are at a very early stage for that. For AEM and PM and alkaline water electrolyzers, the EU harmonized protocols had some aspects of it in the official document. Most of it is electrolysis as a field itself is slightly less mature, quite a lot less mature than fuel cell technology. Fuel cell technology, both EU harmonized protocols and US Department of Energy, they have published harmonized protocols. We're not at that stage, even for PEM electrolyzers yet. Now, although there are no officially endorsed protocols, what we did, we can share our experience when we are formulating the plan for HySEAS. Is what we did. We borrowed what is publicly available from previous EU funded projects, what they had followed in their deliverables and so on and so forth. We came up with a plan that each partner will follow. I'm pretty sure that's what everyone else is doing as well. I do want to highlight that it's not an easy exercise to come up with a harmonized protocol. The material, as soon as you change one aspect of these membrane electrode assembly cells and stacks, you almost have to re-engineer the entire thing, right? It's a complicated exercise, but hopefully in the next few years, we will have something we can all lean on.
Yeah, I fully agree. I think we are on time. I'm very glad to see that we had questions from the audience and we have discussed them and answered them. So hand over to Milana, please.
All right. So thank you all again for this very fruitful discussion. And I'm sure that alongside your presentations, it has sparked even further interest among our audience to explore the challenges of seawater hydrogen production. We, of course, encourage you to continue exploring also the solutions from the sister projects. And we hope to see you at any upcoming webinars or events organized by the projects. So thank you again for your attention. And we hope to see you soon in other similar events.
Yeah.
Thank you all.
And hope to see you in
Thank you.
September.
Bye.
Yeah.
Bye bye.
Bye.